Hey everyone, it's been a while, but we're back with another class, a little class online recording stuff. The next section that we're going to get into, as we've talked about in class when we started talking about projectile motion, the next portion of this class deals with the topics that we discussed in the first semester, basically, but how we address them and how we deal with them in two dimensions. That leads us to vectors and vector operations. In the previous section on the projectile motion, especially the angle launch projectile motion, we introduced two vector properties or two vector operations. The first one being find the resultant of two perpendicular vectors. The second one being component vectors, and how do we split up a vector into the two vectors that exist along the x and y axis, or the horizontal and vertical, that represent that resultant vector or that resulting motion, velocity, whatever it is. Today, what we want to do is take it one step further, because we're not always going to end up with those vectors that are perpendicular to one another. So we have to figure out a way to find the resultant vector or add vectors that are not perpendicular to one another. And that's where we're going to go today. First thing to keep in mind, we are still looking for a resultant vector, and that means that it's a vector that represents the sum of two or more vector quantities. That resultant vector is still a vector, which means it requires two things. It has to have a magnitude, and it has to have direction. So our resultant vector, whether we're finding the resultant vector of two perpendicular vectors or two non-perpendicular vectors, the answer has to have two parts, a magnitude part and a direction part. When we are looking at finding the resultant vector of two non-perpendicular vectors, or adding non-perpendicular vectors algebraically, there are four steps. First thing we're going to do, we are going to resolve all of the vectors into their components. That's something we've talked about doing angle launch projectile motion problems, especially at the beginning, when we have that object being launched in an angle, and we know it has a horizontal part and a vertical part, and we can use sine and cosine to find what those horizontal and vertical parts are, and that's where, that's what we get into resolving vectors. But when we do that, what we end up with is a bunch of vectors that are either on the x-axis or the y-axis. None of those vectors, in resolving those vectors into their components, we're basically getting rid of the resultant, or the one that's at an angle, and replacing it with the equivalent to one being on the x-axis, one being on the y-axis. When that's the case, all we have to do is add up the x-axis components, add up the y-axis components, and we're going to make those into one big right triangle. And if we end up with a right triangle, we know how to find the resultant vector of a right triangle, use Pythagorean theorem, use our sine, cosine, tangent function, whatever it is, to get our magnitude and direction. So let's run through a couple of examples, and we'll go from there. First example, adding non-perpendicular vectors, practice number 1. It says when an airplane is taking off, it flies a distance of 35 kilometers at an angle of 30 degrees above the ground. Then it flies 515 kilometers at an angle of 22 degrees above the ground. What is the resultant displacement of the airplane from the runway? So first, let's give ourselves a sketch. We're going to start off. There's our ground. And we'll give ourselves an airplane. That's what airplanes look like in my physics world. So the first thing it said was it flies 35 kilometers at an angle of 30 degrees above the ground. So if we go back to our sketch, we'll represent that with, first, we'll go take our airplane, move it like this, and we'll represent that first portion of the trip with this red arrow. And if we label that red arrow 35 kilometers, 30 degrees above the ground. Now it says after that initial part off of the runway, it changes its course slightly, right? So if we modify that, right, we said that it doesn't go quite as steep anymore, and if you've ever flown on a plane before, you kind of experienced this. So then it says, if I remember correctly, it flies 515 kilometers at an angle of 22 degrees above the ground. So if we represent that with our airplane, right, it's going to look something like this, and we'll represent that second portion of the trip with this blue arrow. Labeling that blue arrow, we know that it's 515 kilometers, and it says, and it's at an angle of 22 degrees above the ground. Well, that also means it's at 22 degrees at an angle, or at any line that's parallel to the ground. So, I know we can't do this in the real world, but if we take the ground and move it up to here, right, that would make this angle as 22 degrees. We'll put the ground back where it's supposed to go for now. And it says find the resultant displacement. The resultant displacement, the concept of the resultant displacement doesn't change. It's still the change in position from where we started to where we finished. If we use the purple arrow to represent that, that's going to be a vector that starts here and goes all the way to here. The purple vector representing the resultant displacement, the change in position. It is part of a triangle, and it is the longest side of a triangle, but it is not a right triangle, so we can't use our normal sine, cosine, and tangent functions the way we do on right triangles. But, as we mentioned earlier, there's a way that we can deal with that. If we go back, said the first step in this process, is to resolve all of their vectors into their components. So I'm going to go back to my airplane picture. Okay. For now, I'm going to take this purple one and just move it out of the way, just so we have some space to work with. We'll bring it back in a second. But it says to resolve all of the vectors into their component vectors. Hopefully you remember that this red vector, the 35 kilometers at an angle of 30 degrees above the ground, is actually doing two things at once. That plane, during that initial section, is moving both horizontally and vertically. The combination of those two motions results in it going 35 kilometers at an angle of 30 degrees above the ground. That's the solid red arrow. But we can look at that as a combination of those two dotted vectors that we've drawn in. In the same way, during the second section of this trip, the 515 kilometers, the plane is still moving in two directions. It's moving both horizontally parallel to the ground, but then it's also moving vertically. Those two triangles, the red triangle and the blue triangle, those are right triangles. I know that because if I use component vectors, one of the components, if we take the blue triangle for example, this component has to be horizontal or along the x-axis. This component has to be vertical or along the y-axis. That means if one's on the x-axis and one's on the y-axis, they've got to be perpendicular to one another. If they're perpendicular to one another, we've made a right triangle. And if we've made a right triangle, we can use our regular trig functions. Same thing here with the red triangle. Now, in those two right triangles, we have one angle, we have one side. We can use our trig functions to find the other two sides. So go ahead and do that. use your sine and cosine functions to find the two sides, or the two remaining sides of those triangles, and we'll pick it up from there. All right, up on the screen, I've resolved those two vectors into their component vectors, and we end up with an x and a y. So the next thing that it says when we're adding non-perpendicular vectors algebraically is to add up all of the x and y axis components. The thing that makes this easier is that if we have two vectors that are already on the x-axis, adding them up is just as simple as adding them up. So if we go back to our picture of the plane, there are two of those component vectors that are on the x-axis, or along the x-axis, parallel to the x-axis if you want to think of it that way. And there are two vectors that are perpendicular to the x-axis, or along the y-axis, if you want to think about it that way. If I do a little bit of manipulation, I'm going to take this blue dotted line, bring it down here, take the 477.5 with it. I'm going to take this red dotted line, bring it over here, and I'm going to take the 17.5 with that. I'm going to get rid of a few things, like this, and this. And you'll see that if I bring back my purple vector, which we said represented the resultant displacement, the change in position from the beginning to the end, the purple vector should fit right there. And now if we look, this section, I've created a right triangle with the purple side as the hypotenuse of that right triangle. Just to make things a little clearer, I'm going to clean up my drawing a little bit. I'm going to move this out of the way. I'm going to move this out of the way. I'm going to move this out of the way. This, oh, not that. This. And now we end up with one big right triangle with the vector that we already said was the resultant displacement, the purple one, as the hypotenuse. We know the length of the two sides. We have to do a little addition to figure out what the total length is, but we can do that. So we have everything that we need to find the magnitude of the resultant displacement and the direction of the resultant displacement. So why don't you do that now? We'll come back in a second. when you run those numbers through, you should end up with a resultant displacement of 549.7 kilometers at 22.5 degrees above the horizontal. Hopefully that worked out for you. If not, ask me in class. One more practice problem. Practice problem number 2 says, a group of kids finds an old treasure map in their attic. The map says they should go out to their backyard and start at the sycamore tree. From the tree, they should take 5 paces to the north, 3 paces to the east, and 4 paces to the southeast, which we'll assume is at a 45-degree angle. What is the resultant displacement of the treasure from the sycamore tree? Drawing ourselves a little picture to begin, right? We'll call this the sycamore tree. Some green leaves on the top here, a little green grass. Okay? So it says take 5 paces to the north. So we'll label that as 5 paces. I believe it says 3 paces to the east. So we'll take and we'll make that one here. 3 paces here. And then it says 4 paces to the southeast, which, if it says it's exactly southeast, we'll call that a 45-degree angle. So going back to my picture, I'm going to use green this time, and we'll go that here, and we'll label that as 4 paces. It says, what is the resultant displacement of the treasure from the sycamore tree? The concept doesn't change. The resultant displacement is still the change in position from where we started to where we finished. That doesn't change now that we have 3 vectors. It just means we have to draw the vector from the start of the first one to the end of the last one. So the resultant displacement in this problem is going to be represented by that purple arrow. That's the resultant displacement, the change in position from where we started to where we finished. Going back to our steps for adding non-perpendicular vectors algebraically, it says resolve all vectors into their components. If we go back to our picture, we have this 5 paces to the north trip, but if something's going straight to the north, it doesn't have components. It's straight on the y-axis, in this case upwards on the y-axis. 3 paces to the east. Once again, no components for a vector that's directly to the east. However, this 4 paces to the southeast, right? That one's going to have some components. This one is not along the x-axis or the y-axis, so if something's in between the 2 axes that we have in our problem, in this case the north and the east, it's going to have components. And those components are going to look like this. If we're traveling 4 paces to the southeast, move this a little bit just to clean up our picture here. If we're traveling 4 paces to the southeast, we're traveling both south and east at the same time. So there is 2 components there. It tells us in the problem that because it's directly southeast, we can assume that that's a 45-degree angle, halfway between directly east and directly south. Now, like we said before, because we have an x component and a y component, we know those have to be right angles. We know there has to be a right angle between those 2. Now we have a right triangle where we know the hypotenuse, we know one of the angles, and we can figure out the 2 sides. So do that now. if you remember your geometry, hopefully you do, 45, 45, 90 triangle, the two sides are the same, so whether you use sine or cosine, it really doesn't matter. You should end up with the same number, and that's 2.83. So we resolved that green vector into its two component vectors. Going back to our steps, the second step in the process says, add up, whoa, not that one, this one. Add up all the x-axis components and all the y-axis components. Going back to our picture. To clean some things up, I'm going to take this green vector, pull it out of the way. I'm going to take 4 paces and pull it out of the way. 45 in the right angle, go that out of the way. This is what we're left with. So there are 2 vectors on the x-axis, 2 vectors on the y-axis. Right? The one thing that changes in this problem being that this vector on the y-axis points in a different direction than the blue vector on the y-axis. So what are you going to do there? You're just going to subtract them. Okay? In doing that, the third step of the process says, use those vectors to make one big right triangle. So I'm going to take these 2 and add them together. Right? And I'm going to end up with one big x-axis component. I'm going to take these 2 and subtract them and end up with a final y-axis component. It's going to be smaller than the 5 paces originally because we got to subtract because of the different direction, but we'll still end up with it. Go ahead and figure out the 2 sides. Right? Shouldn't be too hard to do. Figure out what our 2 sides are. And then, just to clean up our drawing a little bit, I'm going to take this out of here, this, just going to move all these out of the way. And you should find that you end up with y-axis of 2.17 paces and an x-axis of 5.83 paces. Once again, this was the total, the blue dotted line was the total of our y-axis components. The red dotted line was the total of our x-axis components. So that should make these 2 a right angle. Now we've got a right triangle that we know the 2 sides of. We should be able to find the hypotenuse to give us the magnitude of the displacement, and also this theta to find the angle of the displacement. So go ahead and do that now. And when you plug that all in, you should end up with a resultant displacement of 6.22 paces at 69.6 degrees east of north. And that wraps up a couple of examples with the idea of finding the resultant vector of non-perpendicular vectors. Remember, 4 steps. First, resolve all the vectors into their components. That only applies, really, if we have something that's not already on the x-axis or the y-axis. Once you do that, add up all the x-axis and y-axis components. Once you've done that, use those to make one big right triangle. Now you've got a big right triangle. You can find your resultant vector. Make sure you're finding both magnitude and direction. We'll do a couple examples in class at the very beginning of class on Monday. Then we'll be on to forces in 2 dimensions, and we'll talk about equilibrium, how that's the same, how that's different.